So, welcome back to our lectures on projective geometry. In this slot, we still will care about the axioms of a projective plane, and we will learn about first and interesting small models of the projective geometry axiom. So, whenever you have an axiom system, a model is called something that satisfies the axioms. So you may already have other mathematical objects, and if you have a certain set of axioms, then models for those axioms are, well, certain concrete incarnations that satisfy the axioms. Let me briefly remind you of the axioms of projective geometry. We learned that a projective plane consists of three things: a set P and a set L. Both of them are considered to be disjoint set, and a relation I that describes when a point is incident to a certain line. So we call this incidence, we call these points, and we call these lines, but remember, these are only purely, well, mnemonic things, so that you can memorize easily what you mean. The real thing is in the formulas. So here is first axiom. If you have 2 points and they are distinct, then there exists exactly one line L that is incident to both of them. If you have 2 lines, then there exists exactly one point that is incident to both of them. And here comes the Richmond statement that there are 4 points such that no 3 of them are incident to the same line. Okay, so how can that be realized? And we already in our introductory lecture saw something about the painters and perspective drawings, and how parallel lines in a scenery become points that are finite in a drawing, and essentially extending points in the usual Euclidean plane by points that represent the points at infinity where lines meet. This is exactly the way to go to extend the Euclidean plane. Those of you who already have heard geometry calcul will know that already very well, because we dealt several lectures with that. So assume you have a portion of the Euclidean plane here, and the Euclidean plane in our usual interpretation immediately satisfies our axiom A1. So if you have 2 points, P and Q, say, there is always one unique line joining them, as long as they are distinct as required by axiom 1. So the points are not the problem, but the lines are the problem. So assume you have a line, and usually if you have any other line, you normally will find a point of intersection. But it may happen that those 2 lines are parallel, and then they will not have an intersection in the Euclidean plane. And what you now do is you say, these lines here, I assume, they go until they are at infinity, but I will formally introduce a point of intersection of those 2, which is a new point that was not existent in the old Euclidean plane. So you won't find it in your drawing plane. It's infinitely far away in one direction, and actually all lines that are parallel should meet in the same point. So you could say, if you have line L here, you could define an equivalence class of all those parallel lines, and this point P here will be a point associated to such an equivalent class. And you do that for every bundle of parallel lines. So here is another bundle, and for that bundle of parallel lines, you do exactly the same thing. You introduce one point at infinity, and you extended your point set. So far so good, but now we're no longer violating axiom 2, but we are violating axiom 1, because there are 2 points, say this point and this point, that do not have a line that joins them. So again we extend our plane and we say, well, all points that we added should lie on a new line, let's call it L-inf, which is the line at infinity. And if we do that, and we do that for every bundle, so say we have another bundle of parallel lines here, then we say, okay, also they should meet at infinity. And we do that for all the infinite possible directions of parallel lines, and we collect all those points in one line at infinity, and then we actually satisfy axioms 1, 2, and 3. So axiom 3, this thing here is rich enough. There are many points that satisfy axiom 3, so I don't want to talk about that. But axiom 1, any two points have a line that join them. So if you have, say, 2 finite points, say this one and this one, there is a line joining them. If you have a finite point and an infinite point, so here and here, there is a line joining them. And if you have 2 infinite points, there is a line joining them. If you have 2 finite lines and they already meet in the plane, in the Euclidean plane, then they have their meet. If they are parallel, they have their point of intersection here. And if you meet any line with the corresponding line at infinity, you get the far point out there. Here's a little copy from the book where I essentially, you should look that up in the book, where I essentially described the extensions of how to formalize that. So this is one model of the projective geometry axioms. Now I want to give you a different model, and this time I want to be really minimalistic. I want to get the smallest possible projective plane. So the smallest possible projective plane, well, what do we need? It will at least have 4 points by our axiom A3, and in a way such that no 3 of them will be collinear. So, but then this means that axiom 1 jumps into place and tells us that there must be at least, for any pair of points, a new line joining them. So you see, if we have our axiom 3 and axiom 1, we get at least 4 points, and we get at least 6 lines. Are we done? No, we aren't. We now violate axiom 2. And we see, if you look at this line and this line, they do not have an intersection yet. And it cannot be one of the points that are already there, because then, no matter how you interpret it, we will either violate axiom 1 or axiom 3. So what do we have to do? We have to extend our plane. So we take those 2 lines and we say there must be a new point of intersection. In the same way, we find out that this line and this line do not yet have a point of intersection. So let's add this one, and also the 2 diagonals that you see here. I say diagonals, but still remember these are just formal or symbolic representations of lines and points on the plane. So talking about diagonals may be a little bit misleading. So take these two lines and take their point of intersection. So now we have already 7 points. We should perhaps think for a moment whether we couldn't have been a little bit more economic by identifying some of those points. It turns out that we couldn't, because if this point and this point were the same, we would have two lines, namely this one and this one here, that would pass through twice the same point, which is forbidden by our axiom. But what you see here now is still one more missing line, because so far these 2 points were not connected, these 2 points were not connected, and these 2 points were not connected. But now we can be economic and say, well, we define just one line that connects all 3 of them. And as a matter of fact, what you see here turns out to be a nice projective plane. Whenever you take 2 lines, just press the stop button on your video and try it out. Whenever you take 2 lines in that drawing, they have a unique point of intersection. Whenever you take 2 points, say this one and this one, they have a unique line of connection. Please press the stop button for a moment and check everything. I want to do a few side remarks here. So one side remark is we have altogether 7 points, and we have altogether 7 lines. And what we also have is that each line contains exactly the same number of points. So each line has 3 incident points, and each point has 3 incident lines that pass through it. So you see, all points more or less play the same role, and all lines play the same role, at least if you consider this kind of count. And I want to at least write down one more formula, that 7 is 2 squared plus 2 plus 1, or let's write it even a little bit more suggestive. Let's write it in the following way. It's 2 squared plus 2 to the 1 plus 2 to the 0, and this 2 here is 1 less than the number of points. And we will find out later on that this is really a general fact. So as I've drawn it here, this kind of look doesn't look very symmetric. But as a matter of fact, and I must tell you that because it's one of those little few real gems in mathematics, that an object like this here, that we just got from our axioms in a minimalistic way, is really a highly symmetric object. And I want to tell you how symmetric it is. First, by making a little bit better drawing. So I replace this object by this drawing, and you can check, again, press the stop button, that this here satisfies exactly the same incidence structure. So I have to tell you how to read it. So each thing that seems to be a line here, so these straight lines here, is really a line, and this thing that looks like a circle is a line in our projective plane. So this is a line incident to these 3 points. And if you check it, whenever you take a line, say this one here, and another one, there is a unique point of intersection. And I promise you, this is exactly the same structure as we have seen before. And what you see from that here is that this structure is more symmetric as we've drawn it in the first picture. So it turns out that it has at least a rotational symmetry of order 3. So there is an automorphism of that picture that maps this point to this one, this point to this one, this point to this one, and this point to this one to this, and this one to this, and leaves this here as a fixed point that maps the structure to itself. There's also another automorphism. Let me just erase these things. Here I don't write down the those points that go to themselves, but you may interchange these 2 points and these 2 points simultaneously, and you get another automorphism. So what you see is that the S6, the symmetric group, no, not the S6, the S3, the symmetric group with 3 elements is indeed a subgroup of that. Is that all? By the way, this object, as many famous objects in mathematics, has a name. It's the so-called Fano plane, and it's named after Gino Fano. And if you look at the dates here, you see that we are rather late here. So people studied finite projective planes mainly quite a while after they studied real projective planes. So I want to give you another presentation, and believe it or not, the picture I've drawn here is again the same combinatorial structure as we had before in the other picture. I tell you how to read it. Here you have our 7 points of the Fano plane, and 3 points are on a line if they are connected by one such curve. And I singled out one of those lines to show you how this line goes. So you have one line here, you have another line here, you have a third one here, and so on and so on. And it may be a little bit difficult to believe that these 2 objects are indeed the same, but they are, and let me just show you that they are indeed. So I really want to label the points in this picture now by 1 up to 7 so that you can see really obviously they are the same thing. So first of all, I told you that 1 to 4 are on a line. So let's start greedily and say, well, let's say this line here should be 1, 2, and 4. So then we have a next line. I rotate this to indicate a next line. So we have a next line 1, 7, and 3. And so let's again be greedy and put the 3 here and put the 7 here and say that this line here is exactly this line here. You see there are only 2 unlabeled points left. So let's see what happens next. We have another line 7, 6, and 2. So let's look here. Here we have 7. Here we have 2. Though the only place where the 6 can be is this line here. So let's continue. We have 5, 6, 1. So we have the 1 here. We have the 6 here. So the 5 has to go here, but still we only have cared about 4 lines, or even 4 lines so far, and still there are 3 lines left, and we have to check whether they are still correct. So let's do that. So we have another line 4, 5, 7, and if you look here, you have the 4, 5, 7 being perfectly collinear in the other picture. And we have even another line, 3, 4, 6. 3, 4, 6 being perfectly collinear in that picture. And we have a last line, 2, 3, and 5. And if you look here, 2, 3, and 5 is our weird line in the other picture that actually looks like a circle. So the 7 lines here are exactly the same as the 7 lines on the other side. So now I rotated once completely around. So you see, these two pictures are actually really exactly the same. I want to show you several more representations of how we could think about such kind of incidence structures. So this here is called an incidence diagram. So in an incidence diagram, we indicate points really by points, and we indicate lines by some kind of connected swirly curves, and we indicate incidence really by incidence. And well, essentially every incidence structure, every projective plane can be drawn as some kind of incidence diagram. Here's a different way of thinking about it. You could also make a table. You could say, well, my points are 1 to 7, and every line A I well consider as a row in that matrix here and make a cross whenever you have an incidence. So our line 1, 2, 4 corresponds to these three crosses. Our line 2, 3, 5 corresponds to these three crosses. And you see I ordered the columns and the rows in a way that this cyclic symmetry really shines through in that matrix. One would call that an incidence table. There's another way of representing such incidence structure. The other way would be what we call an incidence graph, and this treats points and lines a little bit more symmetrically. So we have seen here points were dots in that picture here, and lines were really some curves in that picture. But what happens if we say, well, this here is just two similar objects? So we make a structure where the points are represented by dots and the lines are represented by dots as well. And we indicate an incidence by simply drawing an edge between points of lines. So you get a bipartite graph where points are played by one part of the graph and lines are played by the points of the other part of the graph, and the incidences are indicated by lines between points and planes. And if you check that here, for instance, 2F are connected by an edge, means that 2 is incident to F. So that's another way, and those incidence graphs may sometimes be really beautiful objects. And as a final thing here, I want to show you another way of drawing the incidence graph of the Fano plane. And as I mentioned, the Fano plane is an extremely beautiful object. And so we have two completely different pictures with completely different symmetry properties. And here's the last one. So this here is called the incidence graph. And here's the last one. This here is also a representation of the incidence graph of the Fano plane, this time as a graph on a torus. So what really counts in that picture is what is inside this parallelogram. And what I do here is I identify this edge here with this edge and this edge with this edge. You see, I, for convenience reasons, drawn part of it, copied it over here, and part of this I copied over here, and you will recognize all our 7 points. So you have 1, which is at the corner, and you see all these ones get identified. 2, 3, 4, 5, 6, 7, and you have all the lines A, B, C, D, E, F, G, in that picture, and please press the pause button on your video and check that this is really the same incidence structure that we had in the Fano plane. So essentially you can say the Fano plane has, in a strange mathematical way, the geometry of a torus. Little summary up to that point. We dealt with axiomatics. We saw these three axioms are the basis of everything. We learned about some models, one of them over the real numbers, and we learned about another model, which is essentially the smallest projective plane. And we drew a few first simple consequences. Oops. Wait a second. And what we will do next is we will consider a few first formal consequences from our axioms. See you in our next lecture.